In this video demonstration, I will explain to you how to conduct Pearson correlation in SPSS. The data that we will be using is a dataset that comes from 10 participants who were measured on their aptitude test, and also their exam scores were recorded, and the research hypothesis was that there will be a positive correlation between aptitude test scores and examination scores. If you want to follow the video demonstration with a data file, you need to create a data file in SPSS using this data. The steps of the analysis that we will take is, firstly, we will test the assumption. We will look at the distribution of the variables, we'll screen for outliers, and we'll examine the linearity. Then we will move to the computation of descriptive statistics and computation of inferential statistics. Because Pearson's correlation is a parametric correlation, the computation of descriptive statistics can be requested as part of the actual test conduction. So let's have a look. Once you enter your data should look like this. So you have a participant number, aptitude test scores, and the exam scores. If we look at the variable view, here's all variables are numeric. They have decimal places. I would say remove them, no need for extra clutter in a dataset, and we need to specify that aptitude test and exam scores are both scale variables. So first step, testing the assumptions. If you go to Analyze, Descriptive Statistics, Explore, the new window will open. In here, we'll move the aptitude test and exam scores into the dependent list. Go to Statistics and select Screening for Outliers. Press Continue, and then go to Plots and request histogram and normality plots with tests. Click Continue. So now we're set up to test the distribution of two variables as well as screen for the outliers. Press OK to run the screening. So the output opened, and first we see the case summary. So we have 10 participants, and both of them provided scores on both of the variables. Then we'll move to the descriptive statistic table. The values of interest from this table is the values for skewness and kurtosis. So those are the values. The first column represents the statistics for skewness and statistics for kurtosis, and the second column represents the standard errors. To see if these variables are normally distributed using the scores, you want to take 0.392 and divide it by 0.687. That will give you a z-test results, and if your result is less than 1.96, you can conclude that the distribution of this variable is relatively normal. The 1.96 is used for when your sample size is small or less than 50 participants. So then we have the same values for our examination scores. In here, just by looking at it without even computing the scores, we're unlikely to see any problems. So basically, the skewness of the perfect normal distribution should be 0. And in this case, both distributions look like they are all right. And similar goes for kurtosis. They also look all right. We have the extreme values, which we are not concerned at the moment. This table, test of normality, it shows you the result of Kolmogorov-Smirnov test and Shapiro-Wilk test. They test if distribution of your data is significantly different from the normal distribution. So if the results of the tests are not significant, that means that distribution of your data is not different from normal distribution, i.e., your data is relatively normally distributed. So you want these tests to be not significant. The third point of examination is we want to look at the histogram. So this histogram looks a bit ugly, but overall it's not that bad. It does have in a way a bell-shaped curve. And then we have our box plot. And in this box plot, you'll be able to see if there are any outliers. So if any of the values fall outside this area or this area, they will be denoted by the small circle that will state the row where the data is. It will not state the number, the participant number, it will state the row in a data set. So if it's a circle, that means the outlier is considered using 1.5 rule, and many researchers argue that those people are not really an outliers. If the outlier is denoted by little star, it's best to remove that outlier for the data set. But in here, there is no particular problem. Then we'll look at the histogram of the exam. Again, a bit ugly, but actually not that bad. It looks relatively bell-shaped. And we look at the exam, and again, no outliers. So our assumption of relatively normally distributed variables is satisfied, and there are no outliers in a data set. So the last assumption that we need to check is the linearity of the relationship. So go to Graphs, Chart Builder, and the new window will open. We want to plot the scatter plot, so we drag the first one in there, and then we just simply drag the variables onto the x-axis and to the y-axis. It doesn't matter in which order you put them, exam on the x-axis, aptitude test on one y-axis. It doesn't matter. The relationship will not change because of that. So once you set up, press OK and wait. Here we have our scatter plot, and we can see that overall the way the scores are spread indicates that there is a linear relationship between the two variables, and we didn't see any outliers, so all the dots kind of in a way clustered together. This pattern actually indicates quite a strong positive relationship. So the final assumption of linearity is also met. Therefore, we can proceed to descriptive statistics and inferential statistics. In SPSS, you can compute descriptive statistics separately, or you can compute it as part of the Pearson correlation test. So to compute the Pearson correlation test and descriptive statistics together, go to Analyze, Correlate, bivariate, and we place two variables that we want to correlate into the variables box. Pearson correlation is selected by default for you. Our hypothesis was directional. It specified that there will be a positive relationship between the two variables. Therefore, we need to select a one-tailed test. When you go to Options, it gives you a statistics option as mean and standard deviation. You tick those ones to compute descriptive statistics as part of your Pearson correlation analysis. Press continue and press OK. So here is the result of our correlation. We can see our mean for both of the variables and standard deviations for both of the variables. This is the inferential statistics Pearson statistics table. And what we see in here is correlation coefficient between the two pairs of the variables. So you can read this table either from below 1 in this area or from above 1 in this area. What we have is what 1 denotes. 1 is the perfect positive correlation. And of course, aptitude test correlates perfectly with an aptitude test. Then what we are interested in is how aptitude test relates with exams. I usually read it from the bottom of the table, but it's just my personal preferences. So aptitude test and exam scores correlate at 0.732, and the correlation is significant. So you get your significance at 1 tailed in here, and this significance is also denoted by the stars. If you look at the bottom of the table in its dialog box, it says 2 stars is a correlation significant at 0.01 level. And then you always get the number of participants that were used in computing the correlation coefficient. So in our case, you can see that this box is a mirror image of this box. Therefore, you only read from one side of the table, either above 1 or below 1. So, in order to report this correlation, what we can say about it is that it is positive and it is strong and it is significant. So, to report it, there was a significant strong positive correlation between the aptitude scores and the final exam scores. R in brackets 10 equal to 0.73 and P is less than 0.01, one-tailed test. The additional sentences that you'll need to add to this report is that the assumptions were tested and list the assumptions and state that all the assumptions were satisfied. So you can add a sentence before as a first sentence saying the assumptions of distribution of the variable, the linear relationship between the variables, and also screening for the outliers was performed. The distribution was relatively normal. There was a linear relationship between the two variables and there were no outliers in the data set. Therefore, to analyze data, Pearson correlation was used. Then you state this sentence: there was a significant strong positive correlation between the aptitude and the final exam scores. So because we computed descriptive statistics and need to report it as part of the outcome, you can put means in here: aptitude test mean equals 15 and SD equals 15, and final exam scores with the same pattern, M equals SD equals. So in this case, you can report both descriptive statistics and inferential statistics in one sentence. So you just replace the question marks with actual values, keeping it to one decimal place. And at the end, to conclude the sentence, you'll say, therefore, research hypothesis was supported. So it's very important that at the end of reporting of your results, you always state whether the research hypothesis is supported or not supported. Or in some cases, it could be partially supported. If, for example, your hypothesis included a relationship between several variables and some of them were significant and others not. It's always better to write hypothesis in a simple way, because then you can clearly state if it's supported or if it's not supported. And this is it for conducting a Pearson's correlation.